Hi, this is Melanie Walter. I was one of Miss Snow's Honors Chem students last year, and this is a presentation on equilibrium and ice tables. So, the equilibrium constant is represented as KEQ, and it's a ratio of products over reactants raised to their stoichiometric coefficients. So as seen below, C and D are the products, so they're in the numerator of the fraction, and they're both raised to their stoichiometric coefficients, and also A and B are the reactants, so they're in the denominator, also raised to their stoichiometric coefficients. Also, the equilibrium constant is known as the law of mass action. So one of the properties of the equilibrium constant is that it remains constant through despite different initial concentrations of the reactants. So as seen here, you can start with completely NO2 or completely N2O4 and end with the same equilibrium constant, because the equilibrium constant is just a ratio of the products over the reactants. So in setting up an ice table is really just an organizational tool used to track or calculate the values of reactants and products at equilibrium. So usually in a problem, you're given initial concentrations, and you put those in the initial row, or period, or not period, but yeah. You put those in the initial boxes, and then your equilibrium values will go in the equilibrium one, but you track your changes through the change one. So in an example problem right here, you're given a closed loop system initially containing 1.0 times 10 to the third molar H2 and 2.0 times 10 to the negative third molar I2. And so you'll fill those values in the appropriate box. So for H2, it would be 1.00 times 10 to the negative third molar. And for I2, it would be 2.00 times 10 to the negative third molar. After that, you're given the, so the reactant's allowed to reach equilibrium, and the concentration of HI at equilibrium is 1.87 times 10 to the negative third molar. Then the problem asks you to calculate the KEQ for the reaction. So, the information that you know in this problem is that you have no HI to begin with, but you're given, but at the end of the reaction, you have 1.7 times 10 to the negative third molar. So you're able to calculate or change this by subtracting, because you know you gain 1.87 times 10 to the negative third molar of HI throughout the reaction. From this information, you're then able to calculate the change for both I2 and H2. You have to take into account the stoichiometric coefficient of HI when doing this. And so by calculating this, you'll end up getting negative 9.35 times 10 to the negative fourth. And the way you're able to calculate that is that this should be proportional by the stoichiometric coefficient. And the reason that these two are negative is because the amount of these is decreasing while the amount of this one is increasing. And so in order to calculate the equilibrium for both of these, you just subtract. So for H2, you get 6.5 times 10 to the negative fifth, and for I2, you get 1.06 times 10 to the negative third. Okay, so now on to actually doing the problem. In order to set up, here, I'll leave that like right there. So in order to set up your KEQ expression, it's going to be, again, a ratio of products over reactants raised to the stoichiometric coefficients. So it's going to look like this. KEQ equals the concentration of HI to the second over the concentration of H2 multiplied by the concentration of I2. Oh, not that. I2. So now all you have to do in order to find the equilibrium constant for this would be to plug the equilibrium values of all three of these substances into this equation. So it would pretty much just look like this. So it's going to be 1.87 times 10 to the negative third squared over 6.5 times 10 to the negative fifth multiplied by 1.06 times 10 to the negative third. And that's it. From there, all you need to do is just plug it into your calculator, which would look like this. So this is like, so it would be 1.87 times 10 to the negative third, and then you're going to square that, so that is there. Oops. Sorry. So you're just going to, oh my god. Okay, sorry, that was like, and then now you plug in the stuff in the denominator, which is 6.5 times 10 to the negative fifth, and then you're going to multiply that by 1.06 times 10 to the negative third. And so then you just solve that, and you get 50.75326, which will then, in taking into account significant figures, will end up being 51. So the KEQ for this reaction is 51. And in this case, or just for KEQ in general, there are no units. So yeah, that's just general KEQ. Thank you.